This video will look at the lengths of chords and circles. So you need to be comfortable dealing with the following theorems regarding chords and their lengths. The first one has to do with what happens when two chords intersect inside a circle. It says when this occurs, the product of the lengths of the pieces of one chord is going to be equal to the product of the lengths of the pieces of the other. So in other words, what this is saying is that if I have this circle with two chords, for lack of something better, I'm going to call them a green chord and a blue chord. This says that when you multiply the two pieces of the green chord together, that product is going to be equal to the product of the pieces of the blue chord. So if we take a look at example 1, we'll see how you can use this in order to solve problems. So in example 1, we're given this circle with these two intersecting chords. And again, for lack of something better, I'm going to name them the red chord and the purple chord. And this theorem says that when I multiply the two pieces of the red chord together, so 12 times x, that product is equal to what I get when I multiply the product of the purple pieces together. Or in other words, 8 times the quantity x plus 2. So now distributing on the right-hand side gives me 8x plus 16. Subtracting 8x from both sides tells me that 4x is equal to 16. And then lastly, dividing both sides of that by 4 yields x is equal to 4. Since they were asking me to find x in the problem, I know that I'm finished. So that's the first relationship you need to be very comfortable working with in a circle. The next theorems you have to be familiar with regard chords and a radius. The first one says anytime you have a radius that's perpendicular to a chord, that radius will bisect the chord. So in other words, in this picture over here, OD is a radius, AB is a chord, and since that radius is perpendicular to the chord, we know that it bisects that chord or splits that chord into two equal parts. The reverse of this is true as well. Whenever you have a radius that splits the chord into two equal parts, we know that the angle formed there must be a right angle because the chord and the radius will be perpendicular. And likewise, the perpendicular bisector of any chord will always pass through the center. And that's because the perpendicular bisector of the chord is going to have to be a radius. So let's take a look in example 2 of how we might use this to solve a problem. We're told that the circle has the given diameter, and that diameter is perpendicular to the chord, and they want us to go ahead and solve or find x. Well, I know that if the length of the radius is 5, then I know that the length of this piece right here must be 3, because the 3 plus the given 2 must add up to the radius of 5. So I know instantly that that piece is 3. This is really helpful because now I know I have the purple chord with its pieces that are 8 long and 2 long. I have the red chord, and because the purple chord is perpendicular to the red chord, I know it has to bisect the red chord, making each of those pieces x. And if I apply what I learned up in the first example, I know that the two parts of the purple chord, when multiplied together, must be equal to the two parts of the red chord when multiplied together. So the two parts of the red chord, x times x, or x squared, has to be equal to 8 times 2, or 16. And if x squared is equal to 16, then x can either be positive or negative 16, but I'm going to reject the negative root since my x represents a segment length, and I know that segments can only have length that is positive, and therefore the length of each part of those, or each of those pieces of the red chord, has to be x. And again, I've done what has been requested of me in the problem, so I know that I'm finished. In this next one, it talks about, in a circle, congruent chords being equidistant from the center of the circle, and chords that are equidistant from the center of the circle are congruent to one another. So what this is saying is that since the distance from the center to chord CB is equal to the distance from the center to chord AB, that these two chords have to be congruent to one another. And likewise, it works backwards too. If these chords are congruent to one another, their distance from the center is going to be exactly the same. Let's take a look at how we might use this idea to solve a problem. In example 3, we're told that in circle O, the length of line segment CD is 16. We're told that the length of line segment AB is also 16. We're told that the length of segment OB is 10, and that the segments that are marked perpendicular are actually perpendicular. So the first thing I notice is that these two chords, which I'm going to call the green chords, those two green chords are the same length, and because they're the same length, their distance from the center must be equal. Well, the distance of the first one from the center is OF, and that's going to be equal in length to the distance of the second one from the center, OE. So I know those two red segments have to be congruent as well. Because of the right angles, I know that those radii must bisect those pieces of the chord, making each of those lengths equal to 8. This sets up a nice situation here where I've got this right triangle, where the length of one leg is 8, the length of the hypotenuse is 10, and the length of the second leg I don't know. So for lack of something better, I'm going to call it x. And you might be saying to yourself, but Mrs. McCann, we're not trying to find the length of OE, we're trying to find the length of OF. And to that I would reply, but yes, the length of OE and the length of OF are equal. So if I know one, I know both. So I'm going to go ahead and set up a little a squared plus b squared equals c squared here, making sure that when I substitute into the Pythagorean theorem, the side opposite that right angle is my c squared. So I've got x squared plus 8 squared is equal to 10 squared. So now my x squared is equal to 36, and my x is either positive or negative 6, but again, keeping in mind that x represents the length of a segment, it's going to have to be positive 6. So OE now, if I look at what x represents in the picture, OE is going to have to be 6, but notice that OF has that same length, also equal to 6. All right, we've got one more that we need to worry about here, and that's up at the top of the next page. This says anytime you have parallel lines, they're going to intercept congruent arcs. So in other words, if line segment AB and line segment CD are parallel, then the arcs that live between those two line segments are going to have to be congruent. So in other words, arc AC is going to have to be congruent to arc BD. And this too is an idea that we can use to help us solve problems. In example 4, we're told that these two chords are parallel to each other. So again, I know that the arcs that live between those two chords must be congruent to one another. So I can't call them x because somebody has already used the variable x in that problem. I might call them y. I know that the value of y has to be 40 because that central angle has the same degree measure as that arc. So this piece has to be 40. And now I can write a little equation that says x plus 40 plus 160 plus 40, all of those arcs together have to be 360 degrees. So therefore, the value of x has to be 120. All right, so I'm going to have you go ahead and see if you can apply what you've learned in order to solve the problems at the bottom of that page. And as always, if you have questions, I'm more than happy to answer them the next time that you come back to class.